Welcome to this episode of Transparent Physics, where we will be talking about the atomic fundamentals in preparation for some heavier lifting in our nuclear physics unit. And the first question you might ask is, aren't atoms chemistry? What are we talking about them in physics for? Well, that's an excellent question. In terms of atoms themselves, if you study the history of atoms a little bit, it turns out you will find that there were many contributions to our understanding of the atom that came from the work of physicists. Generally, I kind of like to say that the physicists sort of figured out what the atom was, how it's structured, how it actually works, and then the chemists figure out how it's used in larger combinations in compounds and things like that. But there is no end to really the names of the scientists who are involved in the development of the atomic theory, and lots of physicists involved with that. The Becquerel, both Curies, Pierre and Marie. Now they were sort of chemistry / physics. Marie maybe more physics than her husband was. J.J. Thomson, Rutherford, Millikan, Bohr, Heisenberg, Pauli, Schrödinger, Chadwick, etc. There are a lot of physicists in the history of our understanding of the atom. So it is, I know many of the people watching this probably first talked about atoms in their chemistry class, so you may sort of think that's the case. But it has a lot to do with physics as well. So, all right. That said, again, roughly speaking, I like to sort of consider it that the physicists sort of worry about the structure of the atom itself, and chemists sort of worry about how the atoms interact with each other. And I'm not going to talk much about the chemistry, but if you are interested in learning more about the chemistry, which is again a lot of reactions governed by how electrons interact with each other, there is a series on YouTube called Guillotine Chemistry. The guy's voice may sound a little bit familiar, but it's not me. So check out Guillotine Chemistry for lots of great chemistry videos. All right, so now that that introduction is done, we'll take our cup of tea. Get ready to get started here. And so let's talk about the parts of the atom. So the goal for this lesson is to just get the fundamentals down. If you have a pretty solid understanding of the atom, a lot of this stuff is going to be review for you. That's good. Good review is always nice. And hopefully this isn't new to you, but if it is, I'll do what I can to give you a sense of things to start. Okay, bits of atom. So we're going to talk about the three components of the atom. We'll sort of compare them in terms of their mass, their charge, where they're located, and what it helps you figure out when you know it. So let's we'll do it this way. Add a little more suspense. Okay, so the proton, again, hard to get a scale for what this actually means, but 1.67 10 to the negative 27th kilograms. The negative 27th does mean it's very low mass, not much mass at all associated with it. The charge is what we're going to start with. We're going to call it plus E. There's an asterisk here which indicates we'll have a little bit more to say about that once these get revealed. The location of the proton is inside the nucleus. The nucleus is the center of the atom. And if we know information about the proton, how many protons there are in the atom, it helps you figure out the atomic number. We'll have a little bit more to say about that with vocabulary in a moment or two. Just real quick though, to start, the atomic number is sort of like the social security number of an element. Each element has its unique atomic number, and that's what makes that element that element. So, okay, so 50-50 shot. What do you think I'm going to go to next? Neutrons or electrons? Go ahead, take a guess. Okay, the correct answer is neutrons. So if you guess neutron, good job, 2 points. So in comparison, if the proton is 1.67 10 to the negative 27th kilograms, again, small number, that's all we really need to worry about, very small number. The neutron is the same mass. All right, so the neutron and the proton, both very tiny masses, but they do have the same mass. The charge of a neutron means neutral. You got to watch out. Sometimes people think the N is negative. It's not. N is neutral. and therefore it is zero charge. It has no charge associated with it at all. It also is located in the nucleus, and neutrons help us talk about isotopes, and isotopes I'll have more to say about in a couple moments as well. And then wrap things up with the electron. The electron, in comparison, now again, all these things are small, but the electron is very small compared to the protons and neutrons. It is approximately 1/2000th the mass of the other two. So it takes around 2,000 electrons. Technically, I think it's around like 1860-ish or something. Electrons equal the mass of a proton or a neutron. So 9.11 10 to the negative 31st kilograms. Much smaller than the proton or the neutron, which themselves are very small to begin with. Now, interestingly enough, even though the electron is way smaller than the proton, its charge, while negative, is the same magnitude as a proton. So that's pretty impressive. This big proton has a positive charge, and this very small electron, but the magnitude of the charge of the electron, not the sign, but the amount of charge, is the same as the proton. So it's pretty neat the way that works out. I always thought that was pretty impressive. The electron orbits the nucleus in orbital levels. Again, there's a lot more to say about that in terms of chemistry, electron clouds and uncertainty, and more than we want to talk about in this video. But let's just say for this sake, it's not in the nucleus, it's outside the nucleus. And the number of electrons, essential in chemistry, right now, and we're not even going to worry about this for the moment, but it really helps us talk about ions. And again, ions is another word we'll get to in a moment. In terms of charge, I did mention the idea of E. The E is sort of a standard value, and fundamental unit of charge here for electrons and protons, 1.60 10 to the negative 19th coulombs. Coulombs is unit of charge, named after Charles Augustin de Coulomb. And he's a French scientist. We'll hear from the French again later this video. And if you're interested in learning a little bit of interesting French trivia, after this video, look up the term 72 names in association with the Eiffel Tower and see what you find out. All right. So in the context of talking about protons, neutrons, and electrons, what we see is that there are lots of terms. So let's talk about these terms and put them in context with each other. It's very easy to get these terms confused with each other. Trust me, I've seen my students make mistakes on those all the time, and not because my students aren't smart, great kids. It's just easy to mess this stuff up. So, term palooza. So the atomic number, like I mentioned earlier, is what we sort of consider the social security number of the element. It's determined by the number of protons. So any atom that has the same number of protons, regardless of anything else, is the same element. That's the defining characteristic of the element. Start with hydrogen. Hydrogen has an atomic number of 1. So no matter what else goes on with hydrogen, you know it has 1 proton in the nucleus. Atomic number 2 is helium, etc., etc. Now, similar in sound but different in meaning is the atomic mass. Now, the atomic mass corresponds to the heft of the atom, if you will. And if you remember, we talked about the idea that electrons are much smaller than, I shouldn't say much smaller, much less mass than the protons and neutrons are. So when you go to add all the mass together in a certain atom, we actually ignore the electrons. We don't factor them in. So we just look at the protons and the neutrons. So you take the number of protons, add it to the number of neutrons, and that gives you the atomic mass. Electrons get ignored because they don't make a very big impact on the total mass. Now, one term that I used to get confused about, and actually in doing the research for this video, I learned the official difference between them is the difference between atomic mass and atomic weight. Atomic mass is specific for a certain nucleus. You look at the number of protons, the number of neutrons, and you can take the atomic mass of a certain nucleus that you've got right in front of you. Atomic weight is a broader term. We'll color the nuances a little bit in a moment here, but basically what it comes down to is for given elements, there are variations of nuclei that satisfy the conditions of being that element by the nature of the fact that they have the same proton. And they're not all exactly the same. So when you take the average of all of the atoms in terms of their numbers in protons and neutrons, the atomic weight gives you sort of an average distribution of the number of neutrons and protons in the nucleus. So I don't know, in comparison, there might be somebody standing in front of you who has a height of 6'2". Their specific height is 6'2", but the average height of basketball players might be 6'4" or something. So the idea, well, that's maybe not the best. How about the number of kids in a house? Let's say you might look at a house and there's 3 kids that live in that house, 2 boys and a girl. Now the average number of kids in American households might be, I don't know, 2.1 or something like that. There's no particular house that has 2.1 kids. I mean, the 0.1 kid, what does that mean? The average, when we take all the families that have the 1s and the 2s and the 3s and the 4s and the 17s and whatever, put them all together, blend them together, take the average, you get 2.1. And I'm not saying it is actually 2.1. I don't know what it is, but that's the idea. That's the difference between mass and weight. Mass is specific for a given nucleus. Weight is the average for all the elements. Now that does tie in closely to the next term, which is an isotope. This is an easy one to get mixed up on as well. We mentioned the idea that the atomic number defines the element based on the number of protons. However, that's not the only thing going on in the nucleus. We also have the number of neutrons. Now, you can fuddle around with the number of neutrons and not actually change the element, because the number of neutrons does not determine the type of element or what element it is. But the number of neutrons can shade characteristics of that element. There's carbon-14 and carbon-16. Carbon-16 has 2 more neutrons than carbon-14 does. And they have different properties as a result of it, but they're both still carbon. So the idea is that they share the same number of protons as others of the same element, but they differ in the number of neutrons. And that comes down to the idea of the atomic weight, how you can have a collection of all these atoms of the same element, and when you take the average, you get some decimal answer for the number of protons and the neutrons, because they vary across the spectrum. And the last one, not one that we're going to talk about a great deal, it will become important a little bit later, is the idea of an ion. It will become important in the context of ionization. And an ion is an atom, or it could be a molecule, that doesn't have the same number of electrons as protons. If we make the argument that if an atom has 10 protons, if there are 10 electrons orbiting that nucleus, then you have a positive 10 and a negative 10, and those balance out, and then your net electric charge would be 0. So what we are looking at is an ion is an atom that has a net electric charge, which means it's either gained electrons or given electrons up. And again, chemistry has way more to say about that than I do, because that's a big thing that goes on when you're talking about chemistry. Okay, so that's our sort of introductory segment there. If nothing else, just watch out for the vocabulary, because it can be confusing, the difference between atomic number, atomic mass, atomic weight. Isotopes and ions, kids mix up very easily as well. Alright, so let's flip to the second half of the discussion. And if you were paying attention when we talked about atoms, we mentioned that protons and neutrons are in the nucleus. Now, protons have a positive charge. And as Paula Abdul taught us back in the day, opposites attract, and likes do not attract. The protons hanging out with other protons, if they're both positively charged, they're not going to want to hang out together. So the question becomes, if I'm telling you that the nucleus is composed of protons and neutrons, and the nucleus, we didn't really talk much about the nature of the nucleus, but it's a small, tightly packed little mass in the center of the atom. So you've got these positive charges hanging out together that under normal circumstances would not be hanging out together, because positive charges do not like other positive charges. Well, again, metaphorically speaking. So the question becomes, what keeps the nucleus together? And this is probably the essential question for this entire section, the idea of nuclear physics. The nucleus itself can be an imperfect combination of substances, and that imperfection can lead to it to become unstable. So let's talk about the origins of how that could actually happen. Okay, so as I mentioned, there is some question about how a nucleus would stay together, because a nucleus is composed of positively charged particles, and positively charged particles should repel each other. Now, if you want a term that's named probably about as cleanly as you can name it, we've got the term strong nuclear force. A strong nuclear force is strong, it's in the nucleus, and it's a force, which means it's a push or a pull. In this case, it's a pull. It's an attractive force. So the strong nuclear force keeps protons and neutrons together in the nucleus. Now, neutrons are in the mix here. I'll explain where they come into play. And it's a sometimes thing. It doesn't always work, and we'll talk about why it doesn't always work. Sometimes it's fantastic. Other times it does not hold things together. So we're gonna take a quick diversion. I'm not gonna say a ton about this, but I don't know if you know this or not, but protons, neutrons, and electrons are not the smallest things of matter. People used to think that the atom itself was the smallest bit of matter, and then we realized that atoms were made up of protons and electrons, and then later, thanks to Chadwick, we also found out that there was neutrons in the mix too. And we found out moderately recently in the history of humanity that protons and neutrons themselves are made up of smaller components as well. And that would be another lecture well beyond the scope of what we're going to talk about here. But let's just, it's a fun word to say, quark. So the quarks make up protons and neutrons. Protons and neutrons are made up of combinations of quarks. 3 quarks make up a proton and 3 quarks make up a neutron. It's not my area of expertise, but they have kind of silly names too. But there's called up quarks and down quarks. So a proton is an up, and a down, and a neutron is a down, and an up. And those 3 quarks combine together to make either a proton or a neutron. Electrons themselves are not made up of quarks. Electrons, to the best of our knowledge, they are a fundamental particle. They don't have other things making them up. They are simply electrons. So that's kind of a special thing about electrons compared to protons and neutrons. Now, these quarks have a glue that kind of holds them together. And this is this strong nuclear force that we talked about. So the strong nuclear force is mostly responsible for keeping these 3 quarks together in the form of a proton or a neutron. So most of it is used up inside the structure of the proton or the neutron itself. And so there's very little that sort of makes it outside the radius of the proton or the neutron itself. But there is a small amount of force that does not get canceled out. So if we, I don't even know if I want to draw. If we draw a, if that represents our proton, most of the strong nuclear force is inside of the structure of the proton itself, but little tiny amounts of strong nuclear force are not canceled out in the context of the holding of the structure together, the 3 quarks. And this small amount, it's a small amount. I tried to look up to see what percentage it was. I couldn't figure it out. But it's called a residual force. So it's just the leftover stuff that doesn't get canceled out inside of the proton or the neutron itself. So it's just leftovers, residuals. But that tiny amount of strong nuclear force that doesn't get canceled out inside the structure of the proton or the neutron, that leaks out just a little bit outside of it, can act on other adjacent, next door things. So, maybe this is maybe this is a proton, maybe that's a neutron. So they have to be right next to each other, And then these forces can interact and act as sort of a binding agent to keep these together. But you have to be very, very, very close to the actual object, adjacent really, for it to work. So this leftover force is actually what's responsible for holding the nucleus together. Otherwise, the protons would blow apart. So it's kind of nice that the universe is held together by just a residual leftover, something or other. Now, this is not a perfect arrangement. Protons still don't like protons, metaphorically speaking, and there is still electromagnetic repulsion between them. And the challenge is that while the strong nuclear force is only right adjacent to contact, the electromagnetic force doesn't care. The electromagnetic force acts over a much larger distance. So if we have other protons over here, they don't need to be in contact with this proton to be like, hey, I don't like you. And they all just want to repel each other. So it doesn't matter how far away you get. You can have a proton that's way over here. Now again, imagine this is all part of some bigger nucleus. So you can have a proton that's far away from this proton, but they still are exerting repulsive forces on each other. So you have this, I don't know if a tug of war is the right name for it or not, but there's this conflict between this very localized but strong nuclear force that holds these particles sort of together, and then an over longer distances force of repulsion between the positive charges. Now, the neutrons themselves are not affected by, protons do not repel neutrons. So neutrons are handy because they provide some of this glue, because they do provide some of this residual strong nuclear force. But they do not add any conflict generating positive V positive repulsion. So neutrons are handy to have in the nucleus. And we'll see that as the nucleus gets bigger and bigger and bigger, you need more and more and more neutrons trying to keep everything together. So, but as the nucleus gets bigger, it's harder and harder for the strong nuclear force to hold it all together. This repulsion continues to grow. As you get bigger and bigger and bigger, you add more protons, and the amount of repulsion just continues to increase. And sometimes it simply cannot hold things together. The repulsive forces between the protons are just too great. When that happens, we have what we call an unstable nuclei. Well, this is, I shouldn't say unstable. Nuclei is the plural of nucleus. I should say an unstable nucleus, or unstable nuclei, plural. So, beyond the scope of this lesson is the idea of explaining, when this works and when it doesn't. But we'll just state for the record that some combinations of protons and neutrons just don't work out. They're not stable. And it doesn't have to be a ginormous number of protons and neutrons. You can have a small number of protons and neutrons and it still be unstable. So it's not just giant arrangements. Some small arrangements are also unstable. And these unstable arrangements will randomly try to make themselves more stable. I don't know, metaphorically speaking, imagine that there is a boat or something like a raft, and there's a bunch of people standing on there. Like, imagine a boat, but it's like turned upside down. All right, so it's not the right way. So the hull is facing up out of the water, so it's very unstable arrangement. And there's like 13 people on it trying to stay up because the ship went down or something like that. And maybe 13 people is like too many. It's too many. Everything's going to capsize. So if one person jumps off, that might make the remaining people able to work together well enough that it becomes a more stable arrangement. Or maybe you have to dump 2 or 3 or 4 people for it to be stable. Radioactive decay is kind of like that. The idea is that over time, nuclei that are unstable, and we're not talking about what makes them individually unstable for their individual circumstances, we will just extend the argument that some of these combinations are unstable. So unstable arrangements will, over time, make an effort to achieve a status of more stability, often by ejecting matter and or energy. And it's sometimes more than one step. Sometimes it has to eject some matter and then some energy, and then some matter, and then it has to go through several steps. That's called a decay chain. until it reaches a point where it is a stable isotope, where it doesn't feel the need to decay any further. And we'll have a little bit more to say that in a later video. There's a pretty cool chart that shows you the circumstances under which that happens. Now, radiation and radioactivity was discovered late 1800s, and one of the early pioneers in it, Becquerel, was the one who is given credit for actually discovering the phenomenon. The Curies went in and did a lot of early research on it, and Marie Curie is given credit for terming this phenomenon radiation, observing that radioactive samples emitted rays of energy, and the term ray is associated with gleam, shine, beam, etc. So it's sort of the beams, the rays of radiation coming out of, the rays of energy coming out of this unstable item. That's why the term was given radiation. And therefore, any atom that is unstable, any nucleus that is unstable and emits radiation is considered to be what we say radioactive. And that's all something, if something's radioactive, that's all it means. It just means it has a nucleus that at some point in the future will randomly eject matter or energy, probably, in an effort to make itself more stable. Now, there is a little bit of potential confusion here, because we as a society get worried when somebody mentions the idea of radiation. Radiation is unfortunately a term that's used two different ways. There is the stuff that we're talking about, I'll often try to preface as calling it nuclear radiation. Nuclear radiation is matter and or energy that gets ejected from an unstable atomic nucleus. Now, there is another type of radiation, electromagnetic radiation. Now, that's like the electromagnetic spectrum. You may remember that from other science classes. Ultraviolet, infrared, X-ray, gamma, a spectrum. There is a TED-Ed video that talks a little bit more about the differences between nuclear radiation and electromagnetic radiation. I'll try to link that in the comments of this video. You can take a look for a little bit more of a nuanced discussion of the difference between nuclear radiation and electromagnetic radiation. But that does offer sometimes some confusion when we're talking about this, because people assume the word radiation automatically means bad and dangerous, and that can actually, fancy word, obfuscate what we're really trying to talk about in terms of the science. Okay, so we'll end up with a fun little story at the end. There is a point where there is the inability to have a stable nucleus, where the nucleus just becomes too big. Too many protons battling each other, trying to push each other apart, and there's no number of neutrons that we can keep on tossing in there to add the stability we need to make it good for the long term. And in terms of when that occurs, there is a cutoff. And the winner, to the best of our knowledge right now, is lead. Lead, atomic number 82, is the last element that we know of that has a stable isotope. That doesn't mean that all of lead's isotopes are stable. It is the last element to have a stable, any stable isotopes at all. Beyond that point, kudos if you know what element 83 is. Any guesses? It's bismuth. Fun little story. Back in 2003, the year of the hit single from Beyonce, Crazy in Love, if we want to date it a little bit. In 2003, there was a group of French scientists who did some research, and in 2003, when Beyonce was writing her hit "Crazy in Love," she was writing it in a civilization that thought that actually the last stable element was bismuth. So if you were in a science class in 2002 or early 2003, and your science teacher was talking about stable elements, they would have mentioned that it was bismuth. Bismuth was considered to be the last element that had any stable isotope. And back to the French again. The French in 2003 discovered that the isotope that they thought was stable was actually unstable. B209, when we talk about an element like that, and actually I think, I don't have it handy, I think B is boron. I think bismuth I should probably be writing as, I shouldn't be doing this online, I apologize if I'm wrong. I think bismuth might be Bi, not B. I think B is boron. Well, there you go. There's a chance for somebody to complain in the comment thread, then I apologize for that. But I'm going to go with bismuth, bismuth 209. Scientists realized that what they thought was a stable isotope was actually unstable. Now, the thing that I find amusing about this story is that the amount of time it takes for the average bismuth atomic nucleus to decay is on the order of 1.9 times 1.9 times 10 to the 19th years. And that is a very long time. I think the age of the universe at this point is, the scientists think, around 1.4 times 10 to the 9th years. I think it's called 19 years if you're into your scientific prefixes. So this decays on an extremely slow time frame. And I think it's kind of amazing that they were able to discover that it was able to decay at all, because it's so slow to decay. But bismuth is no longer the champion. So the idea is that when we are talking about the last stable element, it is indeed lead, not bismuth. So there we go. Shrug emoji. Sorry, bismuth. You had it for, you had a good run, but now it's lead's turn. Okay. This was a little bit of a longer video here, but a lot of content to go through to get us ready to go to talk about a lot of other interesting concepts and topics in the context of nuclear physics. So I appreciate you taking the time to listen to this lesson, see what we had to say here, and I hope you see things a little bit clearer with the help of transparent physics.